All right. So I have a summary pages here for here, but now it's a. Let me do it one more time. The summary. We are talking about A goes to P, and we want to say this is an elementary, not complicated reaction is complicated mechanism, elementary reactions, which is a part of the components of complex reaction, and each one can be described this way. So, and I'll just give you one example. This is A naught minus KRT. That's the zeroth order. A is A naught multiply exponential decay. That's the first order. And 1 over A minus 1 over A naught is minus, is a KRT. That's the second order. So we all know this, right? Which is it starts from A naught going to this. So that's, and how, depending on the order of kinetics, we are able to predict this. And what about then, the question is now, what about the concentration of your products? And this one implies this, okay? So A is A naught. What about the product concentration? We can call P naught. You know what this usually implies here? You typically put everything reactant and nothing onto the product side in the beginning of the reaction. So this is, okay, that's the best thing. And that also implies another equation now, because at any time A plus P concentration is same as A naught. Right? So therefore, the product concentration, if you want to see that, that is nothing but just A naught minus A that I was able to figure out from the beginning. And you can just finish the rest. And that's the one. And now I'm going to write something equation that is quite actually involved, okay? So I am going to write second order. Okay, so second order reaction is now dA dt minus KR A squared. This is an easy reaction to solve. Okay, I can do that. But what about if you are second order in this way? It's a second order in overall, right? And then you gotta figure that out on how to solve this. And this one is essentially need a little bit of kind of manipulation of this, because you don't want to keep track of two quantities at the same time, just one reference quantities. So what I want to do is concentration A is A naught minus X. Concentration of B is B naught minus X. Change in the A concentration of BT is minus AT dx. Does it make sense to you? This is essentially, you're putting some reference conversion concentration change as an X to reformulate this equation. So this is one of the practice that, okay, I mean, this is easy. Okay, this kind of thing is easy. But now it's a little bit more challenging equation to deal with. Okay? And the insight that you need to develop, and this is a PChem is trying to provide you some example here. And this is an example where I'm going to put X as a value to rewrite this equation in a different formula. So this equation now all of a sudden that looks a little bit familiar. Okay, dx dt, which is a minus sign, is already out, so I can cancel that, so I can just keep the plus kr a naught minus x b naught minus x. Okay. Whether this equation looks more complicated on the left hand side, this is a much easier equation to deal with. If I write this equation in a way, dt dx is k a minus x b minus x. This is something that you have to solve. This is solvable. Okay. This one is, I mean, how you want to deal with the b and a? They are related for the reaction, like A react with B, producing products. And how you want to deal with this? So that's how I'm going to make a manipulation of the equation, and then start to do it. So, the same drill here. Once you have here separation of variable. Okay, so separation of variable means what changes in x. So these two. So a naught minus x multiplied by b naught minus x. So that's your left hand side. And your right hand side is, once again, the simple form, kr dt. So all you gotta do is now figure out how to integrate 1 over a minus x, b minus x, dx integration. How to do that. Right? This is something that we have to figure that out. And it's doable. Okay? Have you guys remember solving this different integration of this kind? You remember that? This is now what you do is it's now is irrelevant here, right? This equation, the math equation that you learn how to solve it is actually can be applied to solving the second order equation for concentration of A and the B at the same time. As long as you can figure out how x is happening as a function of time, you can plug that in and then to solve this. So that's my logic here. And then, okay, so I want to write it in a simple form: a minus x, b minus x. Remember that? This is a minus x minus b minus x with b minus a equal something, right? With a negative sign. So this is how you kind of break this one into two pieces. This one itself, but this one is easy now. This integration of this is natural log a minus x, natural log a minus x with a negative sign in front. So what you do now, over there, the one in the left-hand side, this one, I will do the integration, 0 to t. I guess x is 0 in the beginning, and so the x. So it is minus d concentration A minus concentration, and then it's integration of natural log A naught minus x with a negative sign. This x is 0 to x. So that is same as KR. And you can solve this, and you guys can look at that. My point here is I don't want you to derive this equation. That's not the point here. The point here is for you to understand, once you write this equation, how do I solve this equation? The whole goal is I want to know concentration of A as a function of time, concentration of B as a function of time. And the trick, each differential equation solving has its own trick. And in his cases, what's seeming that this A and B is different, now continue to unify into one simple variable called X. Once you have that portion done, this is just a matter for you to do the following the bookkeeping. Okay? Even I don't want to, and so it's everything here. ln. Okay, so well, second law equation, but I'm pretty sure the general chemistry equation, general chemistry class Chem 2 didn't solve it. This second order equation, which is like this. And then I forgot to say one thing. I just have to say they should be different. Okay? If these two the same, you know how simple it is? I mean, this equation fails. Right? Not only that, if this, although this is true, right? If they are the same, and then now you guys can use your physical insight, and well, then everything is the same. So this is same as dTdA is same as KR A squared. It's the same thing, because if it's true, the concentration of A is same as concentration of B all the time. So instead of writing this, I'm going to write minus KR A squared. Once you have that, you are in business to solve it right away. Right? If it is not, then you have to deal with this. So this is only true when your A initial concentration is not the same as B initial concentration. If they have the same concentration, you can get the same good old second order reaction with just a one variable, and that's easy. It's easy.